Hello, my name is Ryan Sterling, and today we'll be exploring transient conduction in ham. There are two forms of conduction, steady and unsteady, unsteady being transient. With steady conduction, if you look at an object or 2 points within an object, or any number of points within an object, your temperature does not change as time progresses. However, with unsteady conduction or transient conduction, if you look at those same 2 points and whether you're heating or cooling the object, in this case we're cooling it, your temperature varies with time. Some methods that we use to calculate transient conduction include lump sum approximation, one-term solutions, or semi-infinite solids. The lump sum approximation assumes that all points within the solid follow the same time temperature distribution. There are many applications of transient conduction. One application that's most commonly seen is in cooking. Let's say you go to a restaurant and you order a steak. Normally they ask you how well done you want your steak cooked. Well, what they're really asking is how much transient conduction do you want to occur within the steak. Essentially, when you're cooking a steak, the more well done you want the steak, the more brown that it will be as it gets towards the center. This is due to increases in temperature cooking the meat. The more pink you see, the less transient conduction that was allowed to happen towards the center of the meat, meaning they stayed at lower temperatures over time. They never reached a temperature that allowed it to fully cook to a brown. Now, for certain cuts of meat, they require a specific center temperature for it to be fully cooked. So whether this be like a roast or a ham, you have to allow transient conduction to occur all the way to the center until it reaches this final centerline temperature. So to test this theory of transient conduction, I decided to cook a ham. I took a ham, stuck a thermometer towards the center of it, and took the initial temperature, put the ham in the oven, and allowed it to cook until it reached to its cooked centerline temperature being 160 degrees Fahrenheit. This took approximately an hour and 49 minutes until it reached that 160 degrees Fahrenheit. As introduced earlier, there are several ways to calculate transient conduction. One of those being the lump sum approximation. However, in this case, our BIO number ended up being greater than 0.1, and so the next most accurate method would be one-term solutions. We treated the ham as a cylinder of the shown dimensions and mass. The properties of the ham were found with various online resources, many of which were found from published research papers and cross-checked with online or data available found online, and used their equations for non-dimensional centerline temperature and the Fourier number to calculate for the time to cook. Rearranging the equations and throwing it into a spreadsheet, we were able to calculate an average cook time for the ham to reach a centerline temperature of 160 degrees Fahrenheit of an hour and 48 minutes. Now, the convection coefficient for an oven can range from about 15 watts per meter Kelvin to about 30. So I decided to take each one of those convection coefficients and evaluate the ham for its cook time at each of those convection coefficients and average it out just so we can get an average time. And as you can see, it turned out to be that hour and 48 minutes. Comparing that time to the experimental time, there was approximately a 1% error between the two methods. In conclusion, the time to reach the cooked centerline temperature of the ham was approximately an hour and 49 minutes. Comparing this to the average time to reach the centerline temperature found using one-term solutions, it was approximately an error of 1% between the two methods. This includes that one-term solutions for transient conduction is an appropriate method to use when calculating the time to reach specific centerline temperatures of at least cylinders and other objects.